Tutor, where school is made simple. Let's go.
In today's video, we're going to look at a topic in calculus known as Riemann sums. Now, Riemann sums introduce an interesting idea that we'll look at much more, over the next few videos. But we want to try to approximate the area under the curve of a graph, of a function. And when I look at this, I have three types of rectangles I can draw to help me approximate the area under this curve. I can start with what's known as a left Riemann sum, which is where I start and get the height of my rectangle from the leftmost portion. Now, looking at the first section here, there is no rectangle here because the height is 0. Therefore, there could be no rectangle. Looking at my second one, I find my length on the left. Looking at the third one, length on the left. And then finally, for the fourth one, the fourth section, I find the height by finding the function on the left. And this is what's known as the left sum. They do a corresponding right sum, where I take the height of the rectangle to be the rightmost endpoint and its point on the function. With this in mind, I can see that for this graph in particular, the left side will drastically underestimate the area under the curve because all this white space is unaccounted for, which I can see because the actual area is 5.75, but the estimated area is 4.52. If I look at the right side, well, this clearly overestimates it on this graph. The midpoint would seem to have some balance to it because the left side seems to balance out what's not included on the right side. But this is not true for all graphs. For example, if I were to look at this graph, which is the square root of the absolute value of x minus 1. Notice that the left side on my first section is overestimating, while on the right three, the left endpoint is actually underestimating. So we see that the shape of the curve is going to affect which of the three options we should use. And we cannot automatically assume that the left is going to underestimate and the right is going to overestimate. We have to look at the shape of the curve and see how it fits in. But going back to our original example here, what's critical to note here is that regardless of what we choose as our method of estimation, whether it's left, right, or midpoint, as we increase the number of intervals, the number of rectangles used to approximate the area, we see that the estimated area is approaching the actual area. If I add more rectangles, I see that the approximation gets even closer and closer until I reach out to approximately 70 rectangles under the curve. And notice that a lot of the white spaces disappeared, and my estimated area is 5.69 versus 5.75 actual. So let's look at this if we were doing the same thing for the endpoint. Well, when I look at the midpoint, I start off with 5.80 versus 5.75 actual. So there's a bit of overestimation here. Let's add a few more rectangles. And we see that very, very quickly, by the time we get to 20 rectangles, we've gotten down to 2 1,000ths, 0.002 of precision. So it's a very good estimate at this point. And as I move further out and add more rectangles, now I've gotten it out to 3 10,000ths, which is significant, very, very significant. So why are we using this? Well, this is the entrance into what we call integrals. And as we make more and more rectangles, we're making the width of each rectangle smaller and smaller. And if we were to say have an infinite number of rectangles, then the area of each rectangle would be infinitesimally small, or approaching zero. And we're going to start to see a limit definition approach here, where we convert the sum of all these rectangles into what we call an integral. But that will be a future video.